My name is Daud Ahmed. This is the first lecture of the series on graph neural networks. This is all machine learning. Graph neural networks are a type of neural network. The neural network is a machine learning model that mimics the functioning or the processing of the human brain. In the human brain, the neurons are organized and interconnected to make up the nervous system. In the neural network, the artificial neurons are organized into layers to make up the artificial neural network. Suppose this is a neural network with three layers. The first layer has two neurons, the second layer has three neurons, the third layer has one neuron. Each neuron in the first layer is connected to each neuron in the second layer. Each neuron in the second layer is further connected to each neuron in the third layer. The input to the neural network is to the first two neurons, and the output is from the final neuron. Graph neural networks are a type of the neural network that are designed to work on graph data. A graph is a special type of data structure that is made up of nodes and edges. Suppose a social group of four people: Ali, Noor, Bob, and Alice. Suppose Ali and Bob are friends. Ali and Noor are friends. Bob and Alice are friends. And Noor and Alice are friends. Ali and Alice are not friends. Bob and Noor are not friends. We can say that this is a social network of four people. The people or the persons or the humans are represented by nodes, and their relationship of friendship is represented by an edge. So there are four nodes and four edges in this social network. Graph neural networks can be classified into three major types. The graph convolutional network, it is a type of graph neural network that borrows the concept of convolutional operation from the convolutional neural networks. We will look at this later in the course. Graph attention networks, they incorporate the attention mechanism. For example, if this be a graph attention network, the attention mechanism would assign different weights or different importance or different values to each of the nodes. The nodes that have a higher value or higher importance will be distinguished from nodes that have lower value. Graph sample and aggregate or graph sage is a type of the graph neural network that is designed for large scale graph data where there are millions of nodes and millions of edges. Graph neural networks are applied on graph structured data. A graph written as G is defined as the ordered pair VE, where V is the set of nodes or vertices and E is the set of edges. Vertices represent entities in the graph and edges represent the connections or the links between the vertices. Suppose we have three entities A, B and C, and they are connected such that A is connected to B and to C, and B and C are connected. The connections are edges and the entities are nodes. So there are three nodes and three edges in this graph. Two nodes that are connected by an edge are called neighbors. Here A and B are neighbors, A and C are neighbors, B and C are neighbors. So, some data in real world is naturally and inherently represented as graphs. For example, the social networks such as Facebook or Instagram or Twitter or LinkedIn and Reddit are represented by graphs. The user, the person, or the human being using the network is represented by an entity as a node. And the links between different users, friendships, or connections are represented as edges. In chemistry, molecules or the molecular structures are represented by graphs. The atoms can be represented by nodes, and the bonds between the atoms can be represented as edges. Suppose, consider the structure of ethane. This is ethane. It is a molecule. We can represent the atoms by nodes and the covalent bonds by edges. In road networks or transportation networks, the roads connect different cities. The cities can be represented by nodes and the roads can be represented by edges. Graph data is irregular. That means there is no restriction on the number of nodes, number of neighbors a node can have. There is no restriction of the number of edges connecting to a node. Permutation invariance is another property of graphs. It means it does not matter in which order do we list the nodes of a graph. For example, in this graph we can write the vertex set as A, B, C. It does not matter whether we change the order to B, C, A. This property is called permutation invariance. The message passing mechanism is a crucial concept in graph neural networks. Here I have a sample graph that has 5 nodes A, B, C, D and E. Node A is connected to B, C and D. B is connected to A and E. C is connected to only A. D is connected to A and E. And E is connected to B and D. Further, each node has a vector associated with it. Node A has the vector 1, 0, 1. Node B has the vector 1, 1, 0, and so on. This vector of a particular node is called its embedding vector. If the node under consideration is denoted by U, then the embedding vector of U will be denoted by HU. Further, consider the node A. It has three neighbors B, C and D. A set that contains all the neighbors of A, that is B, C and D, is called the neighborhood set of node A. So N of U will denote the neighborhood set of node U. That means N of A is B, C and D because B, C and D are neighbors of A. In the message passing mechanism, each node exchanges information with its neighborhood nodes via two abstractions, the aggregate function followed by the update function. In the aggregate function, each node or the node under consideration will aggregate or combine the feature vectors or the embedding vectors of its neighborhood nodes. Consider this graph, subgraph A, B, C and D. This graph contains the node A as well as the neighbors of A, B, C and D. So this is called the neighborhood graph of node A. By combining the embedding vectors of node B, C and D, we have several options. We can take the average of those vectors. We can take the average, or we can take the maximum value, or we can sum up the values. Let's go with the max value. For the first element in the vector, 2, 1 and 3, maximum is 3. For the second one, 2, 1 and 1, maximum is 2. For the third one, 1, 0 and 0, maximum is 1. It is denoted by mu. This vector can be written as mu. The next step is to update the embedding vector of node under consideration, that is the embedding vector of node A. Again, we have several options. We can add this vector to the node A's embedding vector and get the resultant vector, or we can multiply this vector with this one, or we can take a weighted sum or any other method of our choice. So if we add them, we get the new vector, that is 4, 2 and 2 as the new embedding vector of node A. In the message passing mechanism, this process is continued for each of the nodes in the whole graph by taking each of the node as the node under interest as u, as the node u. And mathematically, we can write the aggregate function as the aggregation of each node V's embedding vector. Node V belongs to the neighborhood set of node U. This is what we did. And the update function uses the message as well as the embedding vector of node U to produce the next value of the node's embedding vector.